Lesson: Fundamentals of Machine Learning Algorithms. Understanding the fundamentals of machine learning algorithms is pivotal for professionals aiming to excel in the field of artificial intelligence and machine learning. These algorithms are the backbone of AI-driven applications, enabling systems to learn from data and make informed decisions. At the core, machine learning algorithms can be categorized into three primary types: supervised learning, unsupervised learning, and reinforcement learning. Each category serves distinct purposes and utilizes different techniques to solve real-world problems. Supervised learning algorithms are designed to learn from labeled data, which means the input data is paired with the correct output. This type of learning is akin to a teacher supervising the learning process, providing the algorithm with the correct answers to learn from. Common supervised learning algorithms include linear regression, logistic regression, decision trees, support vector machines, and neural networks. For instance, linear regression is used extensively in predictive modeling, where the goal is to predict a continuous output, such as stock prices or temperature forecasts. By minimizing the error between the predicted and actual values, linear regression provides actionable insights into data trends and future predictions. Logistic regression, on the other hand, is employed for binary classification problems where the output is categorical, such as spam detection in emails. The algorithm estimates the probability that an input belongs to a particular class, offering a probabilistic interpretation of its predictions. Decision trees offer a more intuitive approach by breaking down decision-making into a tree-like structure of nodes and branches. This method is particularly useful in scenarios where interpretability is crucial, such as in healthcare diagnostics, where understanding the decision path is as important as the decision itself. Support vector machines are powerful tools for classification and regression tasks, particularly effective in high-dimensional spaces. They work by finding the hyperplane that best separates the data into classes, maximizing the margin between different classes. SVMs are widely used in text classification and image recognition, where distinguishing between categories with minimal error is essential. Neural networks, inspired by the human brain's architecture, are capable of modeling complex relationships in data. Through multiple layers of interconnected nodes, neural networks learn hierarchical representations of data, making them highly effective in tasks such as image and speech recognition. In contrast, unsupervised learning algorithms operate on unlabeled data, seeking to identify underlying patterns or structures. Clustering is a common unsupervised learning task, with algorithms like k-means and hierarchical clustering widely used to group similar data points together. These techniques are invaluable in market segmentation, where the goal is to identify distinct customer groups based on purchasing behavior. By analyzing clusters, businesses can tailor marketing strategies to specific segments, enhancing customer engagement and boosting sales. Dimensionality reduction is another critical unsupervised learning application, where the objective is to reduce the number of variables under consideration while retaining essential information. Principal component analysis is a popular technique for this purpose, transforming high-dimensional data into a lower-dimensional form. PCA is instrumental in fields such as genomics, where it simplifies complex datasets, making them more manageable and interpretable. Reinforcement learning, the third category of machine learning algorithms, is inspired by behavioral psychology, where an agent learns to make decisions by interacting with an environment. The agent receives feedback in the form of rewards or penalties, adjusting its actions to maximize cumulative rewards over time. Reinforcement learning is particularly effective in dynamic environments where the decision-making process is sequential, such as in robotics and autonomous vehicles. Algorithms like Q-learning and deep Q networks have shown remarkable success in mastering complex games like chess and Go, demonstrating the potential of reinforcement learning in strategic planning and decision-making. To effectively implement these machine learning algorithms, professionals need access to practical tools and frameworks that streamline the development process. Python, with its rich ecosystem of libraries, is the preferred programming language for machine learning practitioners. Libraries such as scikit-learn, TensorFlow, and PyTorch provide robust implementations of various machine learning algorithms, enabling rapid prototyping and deployment of models. Scikit-learn is a versatile library that covers a wide range of algorithms in supervised and unsupervised learning. Its user-friendly API and comprehensive documentation make it accessible to beginners and experts alike. For instance, scikit-learn simplifies the process of training a decision tree classifier with just a few lines of code, allowing professionals to focus on fine-tuning hyperparameters and evaluating model performance. TensorFlow, developed by Google Brain, is a powerful library for building and deploying deep learning models. Its flexibility and scalability make it suitable for a variety of applications, from image classification to natural language processing. TensorFlow's ecosystem includes tools like TensorBoard for visualization and TFX for deploying production-ready models, providing a comprehensive suite for end-to-end machine learning workflows. PyTorch, favored by researchers and developers for its dynamic computation graph and intuitive design, offers similar capabilities to TensorFlow, but with a focus on simplicity and ease of use. PyTorch's seamless integration with Python allows for a more interactive development experience, making it an ideal choice for experimenting with novel algorithms and architectures. The recent advancements in PyTorch's support for distributed training further enhance its appeal for large-scale machine learning projects. In addition to these frameworks, cloud computing platforms like AWS, Google Cloud, and Azure offer managed machine learning services that abstract the complexities of infrastructure management. These platforms provide scalable resources for training and deploying models, enabling professionals to focus on algorithm development and optimization. Amazon SageMaker, for example, offers an integrated environment for building, training, and deploying machine learning models, complete with built-in algorithms and support for custom models. Addressing real-world challenges with machine learning requires not only technical proficiency, but also a strategic approach to problem-solving. Understanding the business context and defining clear objectives are crucial steps in ensuring the successful application of machine learning algorithms. For instance, in predictive maintenance, the goal is to anticipate equipment failures before they occur, minimizing downtime and reducing maintenance costs. By leveraging historical sensor data and supervised learning algorithms, companies can develop predictive models that identify patterns indicative of impending failures, enabling proactive maintenance scheduling. The iterative nature of machine learning development necessitates continuous evaluation and refinement of models. Techniques such as cross-validation and hyperparameter tuning are essential for optimizing model performance and mitigating overfitting. Cross-validation, which involves partitioning the dataset into training and validation subsets, provides a more robust estimate of model performance, ensuring that it generalizes well to unseen data. Hyperparameter tuning, on the other hand, involves searching for the optimal set of parameters that maximize model accuracy, often employing techniques like grid search or random search. Ethical considerations also play a significant role in the deployment of machine learning algorithms. Bias in training data can lead to discriminatory outcomes, particularly in sensitive applications like hiring and lending. Ensuring fairness and transparency in algorithmic decision-making is paramount, requiring careful selection of training data and regular audits of model performance. Techniques such as algorithmic fairness and explainability tools like LIME and SHAP provide insights into model decisions, helping professionals identify and mitigate potential biases. In conclusion, mastering the fundamentals of machine learning algorithms is a multifaceted endeavor that requires a deep understanding of algorithmic principles, practical tools, and real-world applications. By leveraging frameworks like scikit-learn, TensorFlow, and PyTorch, professionals can streamline the development and deployment of machine learning models, addressing complex challenges across industries. The integration of ethical considerations and strategic problem-solving further enhances the effectiveness of machine learning solutions, ensuring they deliver meaningful and equitable outcomes.